Good morning. Today's lecture, we will go to the motors. So the motors basically can be different things, which can be DC motors or AC motors. Here in chapter 15, we will mainly focus on AC motors. So motors can be DC or AC. And even in DC, there are several types. In AC, several types. But let's focus in the main parts of main categories of them. So AC can be induction or synchronous. And even for induction or synchronous, we can see single phase, three phase, synchronous, single phase, three phase. So there are several types. So here we will focus mainly on induction three-phase, synchronous three-phase. So today's lecture will be about the synchronous three-phase, while next lecture will be about the induction three-phase. However, the single phase, we can say, is a special case of three-phase, because most likely, when we assume the system is balanced, we will take the per-phase equivalent circuits by converting three-phase to single phase. Is this right? Then, basically, that's how most likely single phase will be. And keep in mind, for this course, we will take only a special case. We will assume the perfect scenario, which is balance operation. We will take a special type of the motors and discuss it. So the overall idea about this course is just to tell you about the fundamentals. We will not go in depth. While in depth, this will be in different courses. And basically, this will be in electrical engineering major. But for this course, we will most likely discuss three-phase induction, three-phase synchronous, but with very simple, with the simplest model. Okay, so the motor, as we know, is converting electrical energy into mechanical energy. And the electromagnetic energy converted, or as we know, there is generator from mechanical to electrical, motor electrical to mechanical, and there, of course, we need to have a magnetic field, or we call it air gap flux, or flux, almost the same way. So we will discuss the three-phase synchronous motor, then next lecture, three-phase induction motor, while the single-phase motors are basically when you convert three-phase to single-phase, then that's a single-phase. But anyway, we will not go through the single-phase. We will go only through the three-phase, just these two topics. Okay. Three-phase motor, synchronous motor. So, as we know, in the synchronous, that's only in the synchronous. Previous lecture, we discussed the generator. So the generator, there was coils, or stator, and rotor. Here it's the same way, stator and rotor. So I'm going to discuss the three-phase synchronous motor, which is the same as previous lecture, three-phase synchronous generator. What's the difference? Is the power flow, or the current direction. So basically, we used to have the currents going from the rotor toward the stator, then it will go to the grid. Now, the current is the opposite. It will go into the stator. This will make the rotor rotate. So basically, in the motor, the current will go through the coils A, B, C. And since we have a magnetic field because of the magnets, this will produce a torque and will make a movement, which is the magnet will move or the rotation will move. So the rotor will follow the flux, the air gap flux. Okay? So this is the structure of the synchronous, very similar or the same as the generator. Nothing changed, but maybe the difference is the current direction, or in other words, the power flow. And almost the same equations for the mechanical speed, electrical speed, or synchronous speed, rotary speed. They are the same speed. So if we have the electrical speed, 2 pi times 60, this is in radian per second, or F times 60, this is in RPM. And electrical, this is in RPM. So I prefer to use the simple N for RPM, while simple omega for radian per second. And we know the electrical or the rotor speed equal 2 over number of poles times electrical speed. So if we have 2 poles, this yields to 3,600 RPM, 4 poles, 1,800 RPM, 6 poles, 1,200 RPM, and so on. We already know this. The same way that we discussed before. So the overall working principle of the motor, there are some currents flowing into the stator. These currents that are flowing, this will, and there's a magnetic field, which is the rotor magnets. According to Faraday's law, you have a magnetic field, you have electrical energy or electrical currents. This will produce the third thing, which is moving or mechanical energy. That's how it works, which is according to Faraday's law. And now we have the synchronous. Again, this is synchronous motor. There's other types called induction. So again, like 75% of the motors are induction, not synchronous, which is the motor that we will discuss next lecture. Why? What's the point of this? Recall when I discussed about the generator, the synchronous was suitable for constant speed applications. So when we need to use the electrical motor, how about if the speed is not constant? How can I control the speed? Okay, in the previous or the early invention of the motors, there is no way, or it was very difficult actually. So if you need to control the speed of the motor, then basically go to induction, because induction it's easy to control. So in the old cells or in the previous, or when they invented the motors and generators, the vast majority of the motors were induction, because the induction allow me to control the speed, while the synchronous, it will work only on constant speed. So whenever you have a constant speed applications like water pump, for example, where is make it constant on and off, this can be constant speed application, then it can be fine. Okay, based on what's for the synchronous or the motor, how can I make, or how the synchronous is only controlling the constant speed? We know the electrical speed, or the mechanical speed, 2 over number of poles times the electrical speed. And the electrical speed is 60F, so 2 over number of poles times 60F. In other words, this yields 120F over NP, number of poles. This is the actual speed of the synchronous. So when we connect this to the grid, most likely the frequency is fixed, right? It can be either 60 Hertz or 50 Hertz. Number of poles is related to the structure of the motor, so most likely they are fixed. This yields N to be fixed. Is this correct? That's what's happening. So we cannot control, or it's very hard to control the speed of the synchronous motor. That was, again, in the old science, before the inventing of the power electronics. So as a result, synchronous is good for constant speed application. Good for constant speed application. Applications. Then we say that sometimes, how about the number of poles? Can we change it to make the control the speed? You can do a little bit. You can do it like something like that. So if you do it, you can control the speed in steps. So if you make, for example, number of poles equal to, this yields speed 3,600 RPM. If it is 4, 1,800. If it is 6, 1,200. So with this situation, when you change the number of poles, you can change the speed in steps, like 1,800, 3,600, 1,800, 1,200, something like that, which is not smooth relationship, which means I cannot use it in AV as an example, right? Because it is change the speed in steps. I cannot change it from 0 to something. That's initially, that's what we thought. And also, is there any application that we can use to change the speed in steps? You can say number 1, high speed, number 2, medium speed, number 3, low speed. Have we ever used something like that, high, low, without determining the speed, exact amount of speed? Like fan, right? Sometimes in fan, there is some 1, 2, 3, 4, whatever. So you can change the speeds, but you don't know exactly what's the speed, right? But you can change high, medium, low, whatever. So one example that we can use by changing number of poles so you are actually changing the number of poles. This changing number of poles allow us to control the speed. So I said now it's suitable for constant speed application or changing the speed in steps. Okay, so, and I said, okay, it might not be suitable for electrical vehicles, right? That's what it seems to be. So when the early invention of the EV, they used to use induction. Again, 75% of the motors are induction. Even Tesla initially started using induction. Then, by the power electronics, even the invention of power electronics was in 1970s, or then the revolution 1990s. We start using finding a way to control the frequency of the going to the motor. So this means we can control the speed by changing the frequency, by adding a power electronics device. So, as a result, when we have the power electronics that we can control the frequency, then we can control the speed. So that's why, right now in electric vehicles, you will see a lot of synchronous motors. And they inventing or they modifying on the synchronous motor by adding a motor, it's called permanent magnet synchronous motor, PMSM. And also they modified it and with another updated version or better version by a motor called brushless DC motor. I think you might hear of it. So brushless DC motor, it's actually three-phase AC synchronous motor. Why it's called DC? Why it's called brushless? Because they did some modifications on it. They make it very simple, so it looks like as DC. The way that you are controlling it, very similar way that you are controlling the DC. So it's very simplified version, so you can control the DC motor the same way that you can control the brushless DC the same way as DC motor. But keep in mind, the brushless DC motor is a three-phase induction motor. And right now, in EVs, many EVs, they are using brushless DC motor. So I think in Tesla as well, right now they're using brushless DC. And you can see many EV companies, and also you can see an electric scooter as well. E-scooter, you will see brushless DC motor. So the good way about it, which is lighter weight, smaller size, higher energy density, higher efficiency. And all of it is part of three-phase synchronous motor. It's a special case, or a modified version, but it's actually AC. It's called brushless DC, but it is AC. And it's three-phase. So, again, we have different cases, different scenarios. And right now there is an also modified version called switch reluctance motor. This is more advanced versions, and they are using it for the EVs that require higher speed or higher torque, such that it will go from, for example, 0 to 100 miles or 70 miles per hour within a few seconds. So switch reluctance motor, this is more powerful than brushless DC. But the cheapest way or the most applicable way that we are using it in EVs, e-scooters, or the applications that we call it electromotives, then based on brushless DC. Okay. So how are the machine equations? Again, basically, we will convert electrical energy to mechanical energy. Whenever we discuss something related to the electrical, we will talk about the power. And discuss the power formula. While in the mechanical, we will use torque. The electrical engineers prefer to use power, mechanical engineers prefer to use torque. So there is the torque equation. That torque equation, basically, this is the equivalent circuit of the mechanical parts. Because the electrical part, as we know, it's source and electromotive force, resistor, inductance, etc. Or electromotive force, and there is inductance of the motor, the same circuit that we discussed previous lecture. But for the mechanical parts, this is the machine equation, the equivalent circuit of the mechanical part. Tdev is the development torque at the motor terminals. TL is the load torque. TRL is the rotational losses. Because since there's rotation, there's something like friction, but it's in rotation, so that's why we call it rotational losses, not friction losses. Because we are in rotating motion, then you know better than me on this. After that, there is J is the inertia, then the derivative of the speed. Then if we are at steady states, this means the derivative d omega by dt equals 0, which is no changing in the speed. We will assume the speed is constant or no change. This yields development torque equal to load torque plus rotational losses. This is important formula that you need to write it in your note sheets. The other way, P dev, or the development torque equal, development power equal T dev times omega. And development power, we found it from the last lecture. Do you remember when we discussed the complex power of the generator, which is EF times VAN over XD sine delta? This is the same. We will keep using this. This is for the real power. So this is also the second important formula. Remember, keep in mind, there is a torque power characteristic, P equal T times omega. This is called torque power characteristic. We will assume those are in linear. So whenever we need, again, as I mentioned, the electrical engineers prefer to use power, mechanical engineers prefer to use torque. So what's the relationship? How can I make the conversion between power and torque? By assuming P equal T times omega, or power equal torque times the speed. So this is important relationship. This is not always true, but in this course we will assume it always true. Okay? In real life, it's not 100% correct. So basically, the torque and power characteristics, something like that. There is a linear, then there will be some nonlinear region, something like that, some changes. So basically, we will work here. So here, this is linear region. That's what we'll assume. So we will assume we are at steady state, everything working fine, no problem with that, balanced three-phase system, linear region. So we will go to the optimal solution or the best solution or the ideal solution. That's our target, is to prove the concepts, not to go to more complicated analysis. The more complicated analysis can be different courses. But here, again, to prove the concepts. Okay, does this make sense? So keep in mind, these two equations are very important. Torque developments, power developments. T dev or P dev, again, we mean this, which is the development at the rotor of the motor. Okay, so this is the useful amount of power or the useful amount of torque after removing the losses, after removing the load, or like how the load will be when including the load and including the losses, actually. Now, before going to the example, I would like to go to worksheets associated with the Synchronous. So you can see worksheet number 13, Synchronous motor additional. So here's the analysis. Again, we are dealing with three-phase. In three-phase analysis, let's recall the last lecture when we modified the grid and the generator. We assumed strong grid by removing RG, XG. We assume the resistance of the motor, assuming the motor is well designed. Then the resistance of the motor has been neglected. Then the only element left is the EF, electromotive force, and XD, which is the impedance, or which is the inductance of the motor. Then we have V grid. So we have a three-phase. Therefore, this is how the three-phase circuits looks like, because it's three-phase. Then we will assume it's balanced scenario. Then we will convert three-phase to single-phase. So it will look like this way. So the motor and the inductor or the generator, they are exactly the same circuits. But the difference is the current direction. So here is how is the motor circuit. This is how the generator circuit. So the generator, look at on the right-hand side. The generator, like this way. We know this before. That's what we did before. We EF on the left, VA on the right, the current is clockwise, that's it. While in the motor, we see that EF in the left, VA in the right, the same way, but the current is going counterclockwise. Look at the current direction here, the current direction in motor, direction generation, current direction in generator. So now the current is traveling counterclockwise. That's the thing. So what should I do? Motor and generator, the difference between them is the current direction or the power flow. So you can understand it that in generator, the power will go out from the generator toward the grid. Now in the motor, the current going into the motor or into the machine. That's how we can understand it. Okay, so just keep in mind that you can understand the concept. So the current going into the device, then this is motor. The current going out of the device, this is generator. Okay, does this make sense? Okay, now look at the motor circuits. So the current going counterclockwise because again, this is how the current direction. Most likely, when we do the circuit analysis of the motor, we don't prefer to use the current as counterclockwise. Most likely, we used to assume the current clockwise everywhere in our assumptions. So since we have the current going counterclockwise, we will do some modifications so I can let the current going clockwise. How? By swapping EF and VA. Swap this. So another alternative circuit, here is VA, here is JXC, then here is EF, then the current can travel counterclockwise. Clockwise. Again, why I did this? Just I wanted to make sure the current is traveling clockwise. Then by comparing this one and the generator, you will see they are the same, but the thing that we did is we swapped these two, EF and VA. So in order to draw the motor, the difference between motor and the generator, you can do it in two ways. The first way, reverse the current direction. The second way is to swap EF and VA, but keep the current direction. So you need to do one of those, don't do both. So here, number one, change current direction. And number two, swap EF and VA. Again, please make sure to do one of those. Or in other words, just write this in your note sheet and that's it. So the way that we will use, which one we will use this, which is when we swap, because we prefer the current going clockwise. That's what we will use. Use this. Okay? Because again, we prefer to swap the currents, swap the voltages and VA and EF, so we can maintain the current to travel clockwise. Any questions? Okay, let's go on more formula. Most likely, I'm worried a lot about the efficiency of the motors. So, because the highest efficiency, the better motor performance, right? So for you as an engineer, assuming that you are working with a certain company and you need the company to buy some equipment or some motors. So assume that you are the decision maker, then the electrical engineer in your company come to you and say, we have these 2 or 3 options for the motors. And all of them meet our requirements, which is satisfy the load, satisfy what we need, compatible with us. So which one should we use? Now, someone can say, okay, I need to use the cheapest one. But this is sometimes not always true because we have the efficiency. We need to make sure which is the highest efficiency. Because if you buy a motor with 60% efficiency, then you will lose a lot of money in the losses, right? And this will cause it as heat, overheat, and sometimes this can be something undesired. Therefore, what you're going to do, you're going to say to the electrical engineer, please find the efficiency of each motor. So it will give you the calculation. Then you need to look at the calculation just to check, okay, how's the efficiency of this one, how's the efficiency of this one, how's the efficiency of this one. Then, of course, you will choose the highest efficiency, and you can make it a trade-off between the efficiency and the cost. If, for example, like efficiency is 95%, while another one way much expensive, 96%, then you can say maybe I can choose 95. So it's just a trade-off problem. Then you can do this with several factors. Now, how can I calculate the efficiency? The efficiency is basically P out over P in, the output power over the input power. Okay, what's the input power? It is 3 times VA and IA cosine alpha minus beta. Keep in mind there is 3. Why is 3? Because it's 3-phase. Okay? Because 3-phase, that's why I multiply by 3. The other thing, which is one of the most common mistakes, which is when you calculate VA and IA, do we calculate them as a complex number or as a magnitude? What do you think? As a magnitude. Why? Is there any bar above these quantities? No. Then just keep in mind, substitute this as a magnitude. And by the way, you are calculating the real power. It must be a real number. If it is complex number, real power, then there's something wrong. If you calculate the efficiency, you found the efficiency complex number, this is wrong. If you find the efficiency 1000%, this is wrong. If you find the efficiency negative 5%, this is meaningless, this is wrong. Okay? So the efficiency must be between 0 to 1 or 0 to 100, whatever, if you are calculating a percentage or calculating a number. Now, Pn, the input power, 3 times VAN. VAN, we know VA, but take the magnitude. IA, we know how to calculate it. Just do KVL, then you can calculate IA. Then cosine alpha, which is the angle of the voltage. Beta, the angle of the currents. Okay, how about P out? How to calculate P out? Which is TL, here T sub L. It should be T sub L. It's not T times L, T sub L. Then omega, omega S or omega R, whatever, and such that omega means in radian per second, okay? Then how to calculate omega R or omega S? Basically, it is 2 over number of volts times omega electrical, okay? Then keep in mind the load torque most likely given as constant times omega squared. Omega S or omega R, sometimes they call it as omega R. K times omega R square and P out TL times omega R. And don't forget P dev equals 3 times EF VAN over XC sine delta. P dev equal the torque power characteristic, which is T times omega. Then T dev equal TL plus T rotational losses. We already discussed this in the previous slide. Okay? The last thing, delta. What's delta? We know EF bar equal EF angle delta. So delta, it will be positive if you are in generator. It will be negative if you are in motor. Okay? How recall the power characteristics? Here is power, here is delta. So it will be like this. This means generating power. Or it will be like this. This means we are in motor. Okay? That's the power P div, and that's delta. So it will be positive in generator, negative in motor. Why? Because there is a sine wave, and that sine wave, that's how sine wave looks like, the waveform of the sine wave, while the others, EF, VAN, XD, all of them are constant. EF, electromotive force, this is from the nature of the motor. VAN, it is constant because the grid voltage. XD is the nature of the motor. So I cannot control all of this. The only way that I think that I can control it is delta. So it will be like a sine wave. So I can let it work as generator or working as motor. So this nice feature allow us to use it sometimes in EVs or even in some electric scooters, etc., by calling regenerative braking mode. Basically, when you need to do the brake, so most likely the brake that when you press the brake in EV or a normal vehicle, it will go to the normal brakes, like there's a disc, then brushes. This will mechanical brake, and this will go as losses. This will impact the brushes, so maybe frequently you need to change the brakes, right? And all of this will go as losses because let's assume that you're driving down the hill and you're pressing brakes, This goes as losses. So in EV, there's a nice feature when you are driving. For example, you have, maybe driving down, and you need to reduce the speed. There is no need to use the brushes of the brake. You can let the motor runs as generator. This can be in electric vehicles or hybrid electric vehicles. So this allows us to install or to store, use the energy instead of going as mechanical losses as heat, which impact the brushes. It will go to the generator, then from the generator will go toward the battery. So when you drive down, you will store some energy into the battery, which will make it more efficient. Okay? This has been used a lot in hybrid vehicles and electric vehicles. So again, when you drive down, you need to maintain the speed at 70 miles per hour as an example, while when you drive down, the speed goes 80, 90. So what you do, you press brakes. When you press brake, and instead of going to the mechanical brake, it will go to the converting the motor to be generator. Then it will store it in your battery. Okay? So let's, this is the end of this worksheet. Let's go back to the example. Okay, a 480 volts, 4-pole, 100 horsepower, 3-phase synchronous motor. That's operated at the following condition. Make sure to use the operating condition, don't use the rated condition. So you will see something here, 100 horsepower. Horsepower, recall 100 horsepower, I think 763 watts. Anyway, when we are discussing the motors, we will write horsepower. When we're discussing the generators, we will write watts. Horsepower is when we deal with mechanical things, while watts in electrical things. Okay, so let's do the analysis. The first thing, draw the circuits. So the circuit here is here is VA, JXC, EF. Okay? Now, what are the values? We have JXD as J2.5. What do we know about EF? We have EF 300 volts given in this question. But it is 300 volts. Do we know delta? Don't assume it's 0 because EF is given as magnitude. It's not as EF bar. It's given as EF alone. So as a result, we can say EF is EF angle delta. Then it will be 300 angle delta. So we have delta is unknown. The other thing, we have the voltage as 480 volts. So we can use the very famous formula that we did it a lot, which is we say V line to line equal 480 volts. Therefore, V line to neutral equal 480 divided by root 3. Then it will be 277.1 volts. Then VA will be V line to neutral angle 0 degrees. As a result, it will be 277.1 angle 0 degrees volts. So let's do this, put this in the circuit. It will be 277.1 angle 0 degrees volts. So by looking at this circuit, we know VA, we know JXD, EF, the only unknown is delta. So keep this in mind, delta is unknown. So we need to find a way in finding delta. But let's follow up first with the question, then after that we will see how we calculate delta. So the first thing, calculate the load torque. The load torque is given in this question as TL, let me just forget about the circuit. TL equals to 0.01 times omega r squared. 0.01 times omega r squared. Okay? So in order to calculate the load torque, we need to know omega. Okay, I don't know omega. How can I calculate omega? Recall the relationship omega r equal 2 over number of poles times omega electrical. Okay. How about omega electrical? Do we know it? No. How to calculate omega electrical? Which is 2 pi times f. Do we know the frequency? Is it given? No, it's not. So, since the frequency is not given, we will assume it's 60 hertz. 2 pi times 60, then it will be 377 radian per second. That's omega electrical. Then, as a result, omega r will be 2 over number of poles is given as 4. because number of poles is given as 4, 2 over number of poles, then it will be 2 over 4 times 377. So the answer will be 188.5 radian per second. This is omega r. Now I'm ready to calculate the torque. So I can say the load torque, again, 0.01 times omega r square, which is 0.01 times 188.5 square. So the answer will be 355.3. And what's the unit of the torque? Newton meter, of course. This is the load torque. Now, how about the rotational losses torque? The rotational losses torque is given in the question as 0.0281 times omega r. Then it will be 0.0281 times 188.5. Then it will be as 5.3 Newton meter. So you can say the loss is 5.3 while the load 355.3, which is, we can have an just overall view, which is the losses or the rotational losses or the load, the losses will be less than weight the load, and that's what's supposed to be. Now, how about the total torque, which is the development torque? T dev equal T load plus torque rotational losses. Okay? Then it will be 355.3 plus 5.3, then 360.6 Newton meters. Now, the first unknown done, which is calculating all of the torques. Let me go back to the question and see what else we need to do. So we calculated the torques. The speeds, we already calculated the speed. When we calculated the torque, we calculated the speeds, omega. And it didn't tell me you need to calculate the speed in RPM. It said just speed. If you need to calculate in RPM, you can do it. 120 F over number of poles, or 60 times F, depending on if it's electrical or mechanical. Now, the next thing is to calculate the currents. How to calculate the currents? Basically, the current is going clockwise, so you can do KVL. But the thing here about it, which is we don't know delta, right? We don't know delta. Delta is not given. It's not given. So how can I find delta? If you know delta, you can find IA. Is there any relationship that we can use it to find delta? Let's go back to the worksheet and see, is there any relationship we have that we have delta here? Which is what? PDEV, right? EF is given, VAN is given, XD is given, then sine delta. Okay, do we know PDEV? No. How can I find it? Go to the next equation. PDEV equal TDEV times omega r. Do we know TDEV? Yes, we just calculated it, 360.6. Do we know omega r? Yes, 188.5. Okay, then that's it. That's the equation that we can use to calculate delta. Now let me write it here. Okay, we know PDEV equals to TDEV times omega r. Then it will be 360.6 times 188.5. Then it will be 6,000 or 67,973.1, and the unit, of course, watts. After that, we know PDEV equal to 3EF VA n over XC sine delta. That's the equation. Then in order to find, we can substitute the numbers actually. 67973.1 equal 3 times 300, then 277.1 over XD, which is 2.5 sine delta. Then you can find delta. Delta, when you do the sine inverse, will be 42.95 degrees. But recall, this is a motor, then put a negative sign. Don't forget negative sign in delta because it is a motor. Okay? So it's very important to put a negative sign. Okay? That's delta. Now we just calculated delta. How about to calculate the currents? Let me redraw the circuit. We have VA here, JXD, EF, and here is the current IA. So VA is given again as 277.1 angle 0 degrees. Now EF 300 angle negative 42.95 degrees, J 2.5. Then the only unknown is IA. Then we can do KVL. Let's do KVL, loop 1. Start from the left bottom corner, then travel clockwise. Negative VAN plus IA JXD plus EF equal to 0. We need to calculate IA. So IA will be VAN minus EF divided by JXD. Then it will be 277.1 angle 0 degrees minus 300 angle negative 42.95 degrees divided by J 2.5. Then I think IA will be 84.94 angle negative 15.72 degrees amperes. That's IA. Okay, does this make sense? Now the next thing is to calculate the efficiency. How can I calculate the efficiency? You can go back to the worksheets and you can follow the procedures. So let's go back to the worksheets. Let me wait a few seconds to write, then we'll go to the worksheets. Here's the worksheet. Efficiency P out over Pn. This is Pn, this is P out. So we need to do all of these calculations. So here is the procedure written. And you already have your note sheet, so you don't need to worry about memorizing these formulas. So how to calculate the efficiency? According to the worksheet, it is P out over Pn. Keep in mind, all of them must be real numbers. If they are non-real numbers, then there's something wrong in your calculations. So what's P outs? P outs equal load torque times omega r. Load torque we calculated as 355.3 times omega r 188.5. Keep in mind, load torque, not dev torque, development torque. It is load torque. Then it will be 66.974 kilowatts. Or in other words, let me write it as watts. 66.974 watts. Then how about Pn? Pn, it is, according to the equation, 3 times VA, IA, cosine, alpha A minus beta A. That's the equation. So 3 times VA, 277.1. IA, we just calculated as 84.94. Keep in mind, substitute only the magnitudes. Don't put the angle. Don't put angle negative 15. And here, cosine of alpha minus beta. Alpha is 0, beta, which is minus negative 15.72 degrees. So again, substitute only magnitudes. Don't substitute the angles. If you substitute the angles, this yields to a complex numbers of real power, which is incorrect, and this yields to a complex efficiency, which does not make sense. Okay? We cannot say the efficiency is 95% angle 10 or something like that. This does not make sense. And keep in mind, the efficiency cannot be all as well like a negative number. Now we calculate it after we plug this in the calculator. This yields to 67,970 watts. Then plug these numbers, P out over Pn, which is P out 66974 over Pn 67970. This will be 0.8985, and according to the percentage, you can multiply by 100, so it will be 98.5%, which is good efficiency, right? Good. The last thing that we need to do is to calculate the power factor. So the power factor, which is cosine of the angle of the voltage minus the angle of the currents. Angle of the voltage of what? Of the source. So it is cosine of angle of the source 0 minus angle of the current negative 15.72. Then it is cosine of positive, because negative will make it positive, 15.72 degrees. Then plug this in the calculator, will be 0.963. And is it leading or lagging? Positive means lag. Okay? Then this is the end of the question actually. Calculate the efficiency power factor. And I'm going to write some textbook problems about the induction synchronous motor. Textbook problems 15.19, 15.23, 15.24. Okay? Any questions? Now here I want you just to notice, to look at something. Power factor efficiency 0.85 or 98.5. Power factor 0.963. Okay. What's the relationship between this? What's the difference between power factor and efficiency? Efficiency related to the losses. Losses goes as heats. Okay? Which is basically, sometimes that's why when you see the motor, when you turn off the motor, it will be very warm, because losses goes as heat. Efficiency goes to, again, the losses existence, because rotational losses, the internal resistance of the motor, this will cause some losses as well. That's how, from where getting the efficiency. How about the power factor? The power factor will tell us the most efficient usage of the energy. Usage of the energy. It's not related to the losses that we will hear, which is how's the efficiency usage or the most efficient usage that we are using it for the energy. Okay, which is related to, do we use it well or not? And this is related to the inductance, while related to the inductance or capacitance effect, while the efficiency related most likely to the resistance. Okay? Any questions about the synchronous motor? So the next lecture we will start the three-phase induction.